You ever stop and think, like really think about Earth? I mean, it's just there, right,
Yeah.
under our feet.
Right.
But then you start digging into it, like with these Wikipedia excerpts you sent,
Hmm.
and suddenly this everyday thing we call a planet is full of surprises.
Well, you definitely picked some intriguing excerpts. The etymology of Earth and its physical characteristics. It's like you're trying to get to know the planet on a personal level.
I love that. And it's funny you should say getting to know because that's where I thought we'd start with the word Earth itself.
Okay.
Turns out it's way more than just a name.
Right. It can be traced back to the Old English Eoria,
Yep.
which has similarities to words in other Germanic languages.
You mean they're all, like, related?
Exactly. It suggests a common ancestor, perhaps even the Proto-Germanic goddess who represented the Earth.
Whoa, hold on. A goddess?
It's a theory, but it's fascinating to think about how these ancient cultures might have personified the planet.
That's way cooler than just some random word, that's for sure. But you know what else I found interesting? How we write Earth now in lowercase. It wasn't always that way, was it?
Good catch. You're right. For centuries, it was often capitalized, like a proper noun.
Like it was someone important.
Exactly. And that reflects a totally different worldview. Back then, Earth wasn't just a planet. It was the center of everything, possibly even divine.
So the capitalization was like a sign of respect, almost.
You could say that.
Yeah.
It wasn't until science showed us that Earth is just one of many planets orbiting the sun that lowercase became the norm.
Wow. So even just the way we write the word Earth tells a story about how our understanding of the cosmos has evolved. That's amazing. Okay, but enough about words for now. Let's talk size. I mean, we know Earth's big, but when you see the actual numbers, a diameter of almost 13,000 kilometers,
It's hard to wrap your head around.
yeah, it's like, how do you even begin to picture something that massive?
It helps to compare it to something we're more familiar with. Think about Mount Everest,
Okay, Everest. Got it.
the tallest mountain on Earth, a towering 8,848 meters high.
It's hard to imagine anything much bigger than that.
And yet, on the scale of the entire planet, Everest is practically microscopic.
You're kidding.
I'm not. The Wikipedia article said if you shrank Earth down to the size of a billiard ball, Mount Everest would be.
Let me guess. Like a little speck of dust.
Even smaller, maybe a tiny scratch on its surface.
Okay, that's a visual I can actually grasp.
Yeah.
It really puts things in perspective, doesn't it?
Definitely. All those things we consider huge mountains, canyons, entire continents, they're just tiny features on a massive, ever-changing surface.
Ever-changing, yeah. Speaking of which, your excerpts also mention some pretty extreme terrain, like the Mariana Trench.
The deepest part of the ocean.
Yeah. It makes Everest's height look tiny in comparison, right? Something
Oh.
like 11 kilometers below sea level. It's incredible that our planet has such extremes. You know what else I found fascinating?
What's that?
You know how we always think about being far away from Earth's center as being on top of a mountain?
Yeah.
Like the higher you climb, the further away you are.
Right.
Well, it turns out a volcano actually holds that record.
You're talking about Mount Chimborazo in Ecuador.
Yep.
Yep.
It's not as tall as Everest, but because Earth bulges at the equator.
Its summit is actually the furthest point from Earth's center.
That's crazy, right?
It just goes to show that even simple concepts can get complex when you factor in Earth's unique shape.
I am loving all these little aha moments.
Mm-hmm.
So we've talked about what we see on the surface, but I'm dying to dig deeper, what's going on beneath our feet. The Wikipedia article mentioned something called tectonic plates. What are those exactly?
Imagine Earth's outer layer, the lithosphere.
Lithosphere. That's a mouthful.
It's just the scientific term, but picture it like a cracked eggshell.
Okay, cracked eggshell. I'm picturing it.
Each piece of that shell is a tectonic plate, and these plates, they're constantly moving around.
Moving around.
Because of the heat inside Earth, it creates these currents in the mantle.
The mantle.
The layer below the crust. And these currents, they push and pull on the plates, making them drift, collide, even pull apart.
So the Earth is like a giant jigsaw puzzle that's constantly being shaken up.
That's one way to put it.
Wow. And I'm guessing all that moving around has some pretty big consequences, right?
You could say that. That's where things like earthquakes and volcanoes come from. Even those massive mountain ranges we were talking about earlier.
Okay, we are definitely diving into that next time.
Yeah.
Okay, so last time we were talking about how Earth's surface is made up of these giant tectonic plates that are always moving around.
Right, like pieces of a cracked eggshell.
And you said that's what causes earthquakes and volcanoes and all sorts of crazy stuff.
Exactly. It's all about how these plates interact with each other. Think of it like a slow-motion demolition derby, but with continents.
Okay, a demolition derby. I like it. So walk me through it. What happens when these plates bump into each other?
Well, it depends on the type of plates and how they collide. You can have two continental plates crashing head-on.
What happens then?
They buckle and fold, pushing up massive mountain ranges.
Like the Himalayas.
Exactly. The Himalayas are a prime example of two continental plates colliding over millions of years.
Wow, so every time I see a picture of Mount Everest, I'm basically looking at the aftermath of a tectonic fender bender.
More like a slow, drawn-out collision, but you get the idea. It's not just about mountains, though. Things get even more intense when you have an oceanic plate colliding with a continental plate.
Oh, right, because they're different. Right, oceanic and continental.
Yeah. Oceanic plates are denser than continental plates, so when they collide...
The oceanic plate goes under?
Exactly. It's a process called subduction. The denser oceanic plate gets forced down into the mantle, the layer beneath the crust.
And what happens to the continental plate?
It gets scraped and deformed, but stays on top. And all that action at the boundary, that's where things get really interesting.
Interesting how? Like, what happens?
Well, as the oceanic plate dives down there, it releases fluids.
Fluids.
Yeah, water, actually. And that water lowers the melting point of the mantle rock above it, creating magma.
Ah, and magma means?
Volcanoes. The magma rises to the surface and erupts, creating volcanoes along the plate boundary.
So that's why we have that whole ring of fire around the Pacific Ocean. Right?
Exactly. That's a zone where you have a lot of subduction happening, hence all the volcanoes and earthquakes.
Earthquakes, too. Are those caused by the plates colliding as well?
Yep. All that pushing and grinding between the plates creates enormous stress along the fault lines, and sometimes...
It releases...
Exactly. And that sudden release of energy is what we feel as an earthquake.
Okay, it's all starting to make sense now. Mountains, volcanoes, earthquakes. It's all connected to these tectonic plates. But what about those deep ocean trenches we talked about before? Are those also caused by plate tectonics?
They are. They're basically the visible scars of subduction. Think of it like this. As the oceanic plate bends and dives down beneath the continental plate, it creates a deep trench on the ocean floor.
Wow, so we're talking about some seriously powerful forces at work here. But hold on. If these oceanic plates are constantly being dragged down and recycled, does that mean the ocean floor is actually younger than the continents?
You got it. It's like a giant conveyor belt. New oceanic crust is constantly being formed at mid-ocean ridges where the plates are pulling apart, and older crust is being destroyed at subduction zones.
That's amazing. It's like the ultimate geological makeover. So what you're saying is that the ocean floor is constantly being renewed while the continents are just along for the ride.
In a nutshell, yes. The Wikipedia article said the oldest oceanic crust we found is less than 200 million years old.
That's pretty young when you think about it.
Especially compared to the oldest continental rocks, which are billions of years old.
Okay, that is seriously cool. It's like having two completely different timelines playing out on the same planet. So we've talked about the crust and the plates, but what about what's going on even deeper down? Like what's at the very center of Earth? Is it just more hot rock? So we were talking about tectonic plates and all that action happening way down below us.
It's pretty wild to think about, right? All that's going on beneath our feet.
It really is. It's like Earth has a whole other world inside of it.
You could say that. It's a hidden world of intense heat, pressure, and forces that have shaped the planet we know.
And speaking of what's inside, you mentioned that Earth's core is mostly iron. But what about the rest of it? Like, what's the recipe for planet Earth?
Well, it's not as simple as just listing the ingredients. It's more like, imagine taking all these different elements like iron, oxygen, silicon, and putting them in a giant cosmic blender. The exact mix depends on which layer of Earth we're talking about.
Right, because we've got the crust, the mantle, the core.
Exactly. We know the core is mostly iron, but the crust, that's the part we interact with every day, is mostly made up of combinations of oxygen, silicon, aluminum.
Combination, so it's not just pure oxygen like we breathe?
Nope. Those elements combine to form what we call oxides.
Oxides.
And those oxides are the building blocks for all sorts of rocks and minerals.
So like the granite countertops in my kitchen, that's oxides.
Exactly. Or that sandstone cliff you might see on a hike. It's all about how those oxides are arranged.
That's incredible. So Earth is basically made of rock, and those rocks are made of different combinations of elements. But here's what gets me. What keeps everything moving. We talked about the heat inside Earth powering those tectonic plates. But where does that heat come from in the first place?
It's a bit of a mystery, but scientists believe a lot of it comes from radioactive decay.
Hold on, radioactive decay, like the stuff they use in nuclear power plants.
Similar idea, but on a much grander scale. Deep inside Earth, you have elements like uranium, thorium, potassium, and they're constantly undergoing radioactive decay.
And that decay.
Releases heat. It's like a slow-burning furnace that's been going for billions of years.
Wow. So Earth has its own internal heat source, powered by radioactive decay. That's pretty mind-blowing.
And it gets even more interesting. Scientists believe that early in Earth's history, this heat production was much more intense.
Really? What makes them think that?
Well, for one thing, we find these really unique rocks called comatites.
Comatites. Those sound familiar.
They're a type of volcanic rock, but they're unlike anything we see forming today. The magma that formed them was incredibly hot, much hotter than what we see in modern volcanoes.
So does that mean Earth was like a giant ball of molten lava back then?
Not quite, but it was definitely a much hotter and more geologically active place. Those comatites are like little clues left behind, hinting at a time when Earth was a very different place.
It really makes you appreciate how much our planet has changed over time. And it makes me wonder, what's next? What's going to happen to Earth in the far future?
That's the million-dollar question, isn't it? And it's a question that scientists are still trying to answer.
But we do know things will change, right? I mean, nothing stays the same forever.
Absolutely. We know that our planet's fate is ultimately tied to the sun. As the sun ages, it's going to get brighter and hotter.
Brighter and hotter. How much hotter are we talking?
Enough to have a significant impact on Earth. Over billions of years, the increasing solar radiation could lead to a runaway greenhouse effect, causing the oceans to evaporate and making Earth uninhabitable for life as we know it.
So like a Venus situation.
Exactly. Venus is a cautionary tale of what can happen when a planet gets too hot.
That's a bit unsettling to think about, but isn't that billions of years away?
It is, so no need to panic just yet. But it does highlight that our planet is not invincible.
It makes you realize we should probably take care of it while we can.
Exactly. It's a good reminder that we have a responsibility to be good stewards of this planet for our sake and for the sake of all the life that calls it home.
Well said. This whole deep dive has been a real eye-opener. I mean, we started with the word Earth and ended up talking about the planet's distant future.
It's been a journey. And that's the beauty of these deep dives, isn't it? You never know where they'll lead.
That's for sure. And for our listeners, I hope this has sparked some curiosity about the planet we call home. Keep asking questions, keep exploring, and who knows, maybe you'll uncover some surprising facts about Earth too.